Hello. स्टार्ट कर दें. Hello, hello, hello. Okay, so good morning everyone. Today is day 4 and we will start with the lecture number 10. The lecture is about overview of renewable hydrogen based hybrid microgrids, and we are starting 10-15 minutes late due to some issues in the display. So we'll start now. Over to you, Professor.
Thanks, Dr. Animesh, and good morning, everyone. So far, I mean, until yesterday, we have discussed about different, hydrogen technology, including electrolyzer, fuel cell, and then different, DC to DC, DC to AC, and also AC to DC inverter converter. And also we have talked about different control technique that we can utilize for inverter converter system as well. Now, as you see, today's topic more renewable and hydrogen based microgrid. So we already talked about hydrogen. We haven't talked about renewable. So we might do like very basic level discussion, because again that if we want to go very deeper about renewables, it's gonna take maybe another 10 lectures. So we'll touch it, but we'll not go very deeper about renewable energy. So again, most probably you know what is microgrid. So the microgrid is nothing but a smaller version of the centralized power system, right? What we have in the conventional power system, we do have generation, and then transmission, distribution, and then on top of that, different types of loads, control, protection, and so on. So here also in microgrid, we do have generation and different loads, control, everything, but only things that we don't need the long transmission and distribution line, right? Because the area that we design microgrid for supplying power, so the generation and loads are located at the same location, right? So that's one of the advantages, that you don't need to transfer power over long distance where we have got significant portion of the power loss in the transmission and distribution. So that's one of the advantages, but there are many other advantages, because again this is decentralized, it's not like centralized, and also this mainly produce power from renewables, so we don't have greenhouse gas emission as the same amount we do have from the conventional. We might have, but it's very negligible. So that's why it's help to achieve that or to decarbonize, to achieve the net zero target or decarbonize the economy. And this is decentralized as well. And mostly you see that the microgrid is like digitalized as well. So why we need microgrid? As I already mentioned, that it reduces transmission loss, but it's also more reliable, more resilient, and environment friendly. And also there would be many locations, like the country like India and Australia. It's a quite big country, and what happens sometime mainly in Australia, sometimes some in the remote location, only few people lives. I'll show you one microgrid that actually we design and also partially implemented. So only that location have like 40 houses, but to supply that 40 people, they need to build transmission line which like 200 kilometers long, right? And many cases, I mean, those transmission line are quite old. Now they need to upgrade that infrastructure. Now in many cases, what happened, instead of upgrading the infrastructure like building new transmission line or having different sort of new control and new protection and so on, instead of doing that, if you build microgrid, actually is more cost efficient, because you don't need to build that long transmission line. And also what will happen, like when you have got the localized generation, if there is like severe weather event, in many cases transmission line disconnected and they have got blackout. So it's not only cost but also for resilient purpose. I mean, microgrid is getting popular to supply power in the remote area, not only for supplying community, but for mining, or even could be data center. If you have like critical load like hospital, so the application is actually growing in recent years. That's why this technology is getting quite popular in many parts of the world. As I mentioned, like renewable energy is growing, but at the same time, microgrid is also growing. And it's not that, I mean, in most countries, including Australia, I mean, they are actually investing heavily in recent year, because as I did show previously that in many states, they want to have like 70-80% renewable by 2035, 2040. So there are, I mean, so many new project is going on in this area, and the most dominated renewable technology in Australia, mainly the photovoltaic system. And here, I mean, there is a prediction that by 2040 in Australia, 60% of the total power that's going to come from only from photovoltaic system. So now in every 4 house, 1 house they have got photovoltaic system. And also there are many commercially available photovoltaic system available in Australia as well. Now I already mentioned that, I mean, this is not a comparatively new, but I think all of you know like what is microgrid. So I already mentioned that you have got group of generator locally that supply power to the local load, or even it could be that if they have got additional power and if it is grid connected, then it can supply power back to the grid, or if there is a shortage, it can also import power from the main grid as well. Now the size of the microgrid actually could be many different size. For example, let's say if you have got a small building, even in your home, that could be a microgrid, or even like few homes together, or might be that this university campus, that might be a microgrid. So in terms of the sizing, it's not exactly say that microgrid has to be maximum that many kilowatt, megawatt, but you expect that it will be like maximum megawatt range. It's not going to be like a gigawatt range. So it might be maximum like a particular suburb, that could be like a size. But as I say, like a single house also could be operated as a microgrid as well. The component I already mentioned. So, I mean, initially I'll go very quickly because that's, I mean, known facts. So, probably all of you know already, but if someone like, you know, don't have any idea, for them I'll just quickly go through first few slides, then I'm going to slow down when I'll go, I mean, towards more like the research topic. So, I mean, definitely, I mean, it has got generator, and I already mentioned that mostly, I mean, it has got renewables, but in many cases also you will see like, you know, thermal energy source like biogas or natural gas, micro turbine with combined with you know, heat and power, that also you can see in the microgrid as well. But the trend is that mostly now people are thinking to have wind, solar, hydrogen and battery, so that, I mean, you're not using any gas turbine, because still that's not you know, I mean, clean energy source. So, to make it like completely clean, maybe PV, wind, hydrogen and battery, that might be the best option for coming days. In terms of load, I mean, we might have exactly the different appliances load we use. If it is like, you know, community microgrid, but if it is other form of microgrid, you could have like, you know, other industrial commercial load as well. But it also getting, I mean, quite common that the electric vehicle, that could be like a new type of load. But if we use like, you know, hydrogen, a green hydrogen system, then definitely electrolyzer, that's also a new type of load in the microgrid as well. So, energy storage, I already mentioned that so far battery is the dominated energy storage technology in the microgrid, but having said that, I mean, the hydrogen also getting popular, and already I think in Australia we have got 2 operating microgrid with hydrogen and other technology, and also, I mean, there are, you know, other projects in the pipeline as well. So, the point of common coupling, probably this is the word we use many times, but it is the point where probably you already know, like where the microgrid is connected with the main grid. So, this point we call it like point of common coupling. Operating mode, mainly you know, 3 types. It could be islanded, or it could be completely grid connected, or it could be like, you know, the hybrid, that this is like in terms of the operation mode, but also in terms of the DCAC also we have got hybrid. So, don't like, you know, confuse, because here just hybrid means we say like the partially, you know, islanded. I mean, most of the time it grid connected, but also, I mean, sometime it might be, you know, operated isolated as well. So, it's not completely off grid, not completely grid connected, which I am saying here like hybrid, but the normal hybrid definition people thinks both like, you know, AC bus and DC bus. So, when you have got grid connected, in most of the cases the stability is not an issue, because the voltage, frequency, everything, you know, are controlled by the main grid. So, microgrid, I mean, they actually don't think about stability issue. They mostly think about how they can supply power to the like, you know, devices connected with the microgrid, or it, you know, exporting power to the main grid. So, you could also in the microgrid, you could also sometimes have the load management technique, because when you have got like shortage of power in the microgrid, sometime you know, you can have the load shedding option, where the load which are not that critical, you can, you know, turn it off, but load that are critical, actually you can continue to supplying power when there is a shortage of generation. And the critical load could be like hospital, one of the example, data center and so on. And the the battery or hydrogen energy system that can actually support that energy management, like even in like grid connected mode, or even like if you want to do the peak load control, load balancing. So in those cases, I mean, energy storage system that can play a significant role. And again, I mean, this is the islanded when it is not grid connected. So during that time, only the local generation, they're gonna supply power to the local load. I mean, if they have got enough capacity, they're gonna supply all the load. Otherwise, as I say, like you can disconnect it non-critical load from the system. And when it is islanded mode, that time the control and energy management system is quite actually important, because it is actually quite challenging to control the microgrid when it is like islanded, because as you know that most generator are power electronic based. We don't have like any synchronous generator which provide inertia, and also the power electronic device, they are very sensitive. So that's why here we need very reliable and intelligent control to make sure that microgrid, I mean, in the islanded mode, it can operate in stable condition. So in many cases, I mean, as I say, like the islanding can occur either due to the fault, or sometime people just do like intentionally for maintenance and other purposes. So this one, I mean, it could operate, I mean, operate in both mode. So depending on the requirement. And then based on the type of current, either AC or DC. Also, I mean, we classify into AC, DC and hybrid. And again, you probably know already their corresponding advantages and disadvantages. So the DC bus, again, I mean, they operate using the direct current, and as you know, the many of the devices like photovoltaic system, the battery, fuel cell, all produce DC. So if you have got the DC microgrid, you don't need to convert into AC. So that's gonna, I mean, be cost effective, because you don't need inverter. And also, I mean, AC to DC, DC to AC, there are some conversion losses as well. So it will be more like energy efficient as well. But the problem is that for DC still we don't have the protection and other thing as matured as like AC. So that's why for those of you, I mean, working for DC microgrid, the protection is like one of the area. I mean, you still need further research, because the technology are not matured yet. Yeah, so the advantage I already mentioned. And then hybrid, I mean, you have both AC and DC buses, and AC and DC buses are connected using a bidirectional converter, where power can be transferred in both ways. So if any of the buses have got power shortage, it can export power from other buses, or import as well, depending on the I mean, local generation and local load demand. And this is also like one of, I mean, although I mean AC is the most common one you will find, but people now also thinking, I mean, having this hybrid, because as you know that here the advantage would be that you can connect AC generation, AC load in the AC bus, DC load, DC generation in the DC bus. That's why you are actually reducing the conversion from either AC to DC. That's going to make the system more cost effective and more energy efficient. So I think I already mentioned all the advantages, and also people also classify depending on the geographical location as well. So it could be like urban microgrid, like commercial, industrial, campus, institutional, based on like where the microgrid is located. But in terms of operation is quite same. It could be again like whatever classification we have done, it could be any of them. It's just like the location. But sometimes what happen, also depending on the like location, the microgrid needs might be different, because the load characteristics, for example, the university, what will happen? In the daytime, you will need more energy, right? Because most of them, are in the campus in the daytime. But if it is a community microgrid, it would be that, probably you need more power during the evening time, because daytime people are outside. So sometime, depending on the application, your design, your energy management could be different. Another thing also, as you know that the location is also quite important, because as we have like photovoltaic system, wind turbine, and both of them, they generate power depending on the weather, plays a significant role here. So in some area, you will see that photovoltaic system might not be the best option, because it's not that sunny. Even also the wind speed, is not like in the range of around 10 meter per second. Those area, wind might not be a best option as well. So again, that's why location also, determine what type of generation you're going to install in a particular microgrid. Another things, for example, let's say if you have got the microgrid for defense application, then the cyber security, physical security, that would be quite important. But in normal cases also important, but it's not that important as military based microgrid. So if you plan for for military based microgrid, then one of the first option you need to think about how we can make this one cyber resilient. So I think in most of the cases, these are the technology you might be using in the microgrid. So the hydrogen we already discussed. You might already know about rooftop PV. Mini hydro, I'm not sure. Some of might already have idea. Battery also, most of probably you already know about the battery. Then wind also you might know, and then biomass, bioenergy. So that's also could be a source in the microgrid. Anyway, again I'll just quickly go, but any cases, if you want to design microgrid at the end, whatever device you're gonna utilize, at least you need to know the basic modeling. For the designing, you don't need the dynamic model, but at least the steady state power flow model, you need to know, because at the end, for designing microgrid, you also need to forecast whatever energy you're gonna get from all the sources that you're gonna be having in the microgrid. So in many cases, in the microgrid, we do have mini hydro, mainly in the area where you have a possibility to have like lake or anything like that, where you can store water, and also there is some I mean water flow. So if you have like let's say dam like that here, so again you probably know that even I mean how hydro generator works. So possibly just like when water flow from here to here, there would be like a generator, and that water flow will cause that shaft I mean to rotate, and that's how it actually generate electricity from that stored water. And this is the equation normally we use from mini hydro power plant, that what would be the output power for a I mean given turbine. So here it depends on like water density, gravitational acceleration, which is definitely constant, hydraulic head, and then water discharge rate. So depending on this value, I mean you can easily calculate whatever the power that you're gonna get from here. And efficiency again, that will depend on the overall system that you're gonna be having here, turbine generator. So that's gonna give the overall efficiency, and if you multiply that, then you're gonna get I mean whatever output power from that particular system. Now again I mean here like wind turbine, here generator they mostly use like induction type, like asynchronous generator. So for example, it could be that fixed speed induction generator, or even like the doubly fed induction generator. And yeah, you can for steady state modeling, you can be like a constant power voltage, or even like constant active and reactive power. So you can model in this mode, but definitely I mean if you want to do frequency transient instability in the microgrid, where you might have hydrogen plus mini hydro, then definitely we need the detailed dynamic simulation model as well. So it used like again in rural electrification, remote community, like I know like in Australia there is a state in Tasmania where like they have got I mean renewable, but mostly almost like 100% they are coming from hydro. And in this area there is a microgrid, actually they use mini hydro in the microgrid. Diesel, I mean that's not our like desirable option in the microgrid, but in still many cases people use it because they think that when there is no wind and PV and the battery capacity is not enough, they actually keep that diesel as a backup. Normally they don't utilize it, but when there is a need, actually you can actually use diesel. And as I said, like in microgrid still there is a I mean diesel generator. So if probably again like from diesel, like from chemical it's got mechanical, and then from mechanical to electrical using the generator. So again you can model using like voltage, frequency, reactive power equations. Again I mean I didn't give all the equation because it's actually quite available in the literature. So like normal generator, it also have like governor system, exciter, and you can actually control that one either in the PQ mode, giving like constant active, constant reactive power, or like the PV mode, maintains like control like frequency and voltages, where you can give like power, maintains like a constant active power and voltage, mainly in the steady state mode. So how that actually use this fuel in the diesel generator, that again can be determined by this cost function, where P is the power and EBC like the cost coefficient that determine the fuel efficiency, maintenance, and other operational parameters like output of the generators. And there are actually number of methods actually you can easily solve it, and then you can find out the operating cost of the diesel generator for any area, and also how long you're gonna use it and so on. For PV, I mean, although this is not the, I mean, there is like another PV based microgrid, so I'll just skip this one. But again, I mean, that PV normally is modeled like a diode, right? PN junction, so where it depends like not only the radiation but also the cell temperature, ambient temperature, cell temperature, nominal operating temperature of the cell, irradiance I already mentioned, but the shading, but also the temperature actually here plays a quite significant role. How much, I mean, the power that you're gonna get from the photovoltaic system. So if the photovoltaic system actually heated, the output power actually reduce significantly. If you just see like the if you see the equation between power and temperature, and you can easily actually model that one, the relation between output power and as well as frequency. Now for wind turbine, also again, I mean, there is another lecture on wind power hydrogen system. So again, for wind turbine, that's also depend, output power depend on the velocity of the wind, and I'm going to talk this one in the next lecture, but there is a relation between the cut in, cut out, and rated speed. In the rated speed, you're going to get rated power. After cut out 0 and before cut in, I mean, there is relation is given by this equation. So again, I'm going to talk details about the wind hydrogen system in the next lecture. Now, all of the technologies that I mentioned, I mean, it could be a part of hydrogen based microgrid, because hydrogen will be producing from all those renewable sources, and this hydrogen based microgrid, like other microgrid, it does help, I mean, to enhance the renewable energy utilization, because as you know that when there is a surplus renewable energy, you can utilize that one using your electrolyzer. And again, I mean, this also provide pathway, I mean, to utilize in the transportation sector as well. We already talked about using in the refueling station, and also different like both like small car and mostly like heavy vehicle. And when it like stored hydrogen, as you know that we also can be utilized to produce electricity using the fuel cell. Probably we already discussed about modeling of this both electrolyzer as well as fuel cell. So probably you already have the idea, but again, I mean, this is again only for steady state. So here there is no dynamics, and this is comparatively simple equation that's giving the power from like kilogram of hydrogen that I mean you can use. So again, I mean, as we have already discussed, I'll just leave it. You can have a look when you have got the time. Now, what are the challenges? I mean, system integration. So that integrating power to hydrogen, hydrogen to power, and hydrogen storage technology in the microgrid that utilize mostly like in current time, that additional renewable energy, and it definitely has got the potential to transform microgrid architecture when we have got this hydrogen in the microgrid. It definitely introduces new challenges, but at the same time there will be some new opportunities as well. So challenges mainly in the terms of mostly like the operation and control. Now when you gonna actually design microgrid, how we can do that? Where actually we should start? So let's say you have got a new area and you want to build a microgrid. Where you should be starting? What will be the first action point? Modeling the component of the microgrid. That's definitely we need. Anything else? Number of things actually step we need to decide actually before going to deploy the actual microgrid. So I'm gonna quickly go through all the steps, but again I'm not gonna go like very details about this step because all the steps probably you already have the idea, but like all other microgrid, again so I'll just show I'm gonna go back on the previous slide, but so the first thing would be that definitely for the area that you're gonna design microgrid, you need to have good idea about the current demand and also not of the current demand, because microgrid will be designing not for 1 year or 2 years, 5 years, right? It could be like 30, 40 years, right? So things like that you need to know what the current demand and how the demand gonna change in the next, let's say 25, 30 years. And demand modeling also it's not like, oh sorry. Oh yeah, all good, thank you. So in many cases what will happen, although we think that's quite very simple, but when you're gonna go getting time series load data for any community is not that actually quite simple. Now from my experience, the area that actually we worked on, so that area we didn't have any existing smart meter. Then what we did, we installed a smart meter. But after that what happened, the most of the new smart meter, it needs minimum 4G internet connection. Now what happened, that area that we worked on, it was very isolated remote, so they have got 3G. And then we have another problem. We spent almost another 5-6 months to some way having that 4G connection, and then we got that data. So although you think this is quite simple, but when actually you really go to build something in the real cases, you will find a number of problems even you don't recognize. So what I'm trying to say that you need, I mean, definitely you need a very good like load model to find out, I mean, whatever the requirement now, but also what will be requirement later. We also need to develop good forecasting technique. Also not new. There are many technique available in the literature, but again, in many cases, when you have got the system which is very fluctuating, like in many cases you have got fluctuation, either demand or even generation, we found that most of the actually existing technique they fails. When you have got like a good regular pattern, it can actually forecast almost accurately. But when you have got that highly fluctuation, many of the technique actually fails. So I mean, the project that I work on, also I have got the software we actually develop using Python. I'm gonna show maybe the next one. But we actually develop all the tools that actually we need both for designing and operated microgrid. And this is actually very easy, like a graphical tool. You just click on, and then you need to select the input data for any particular area, and then it has already inbuilt different AI algorithm, and it's gonna give you the both short term, long term forecast. So when I'm saying like short term, that means, for example, here we know like the current load demand, what will be the load demand next 5 minutes, and then what would be the load demand next 15 minutes, 30 minutes, not only for demand but also for photovoltaic system, like what gonna output power you're gonna get next 5 minutes, next 30 minutes, next 15 minutes. And when we saying the long term, so for example, let's say up to 2040. So we know like the demand here, for example, let's say, I don't know, maybe 2 megawatt now. What will be the demand in 2030? What will be the demand in 2035? So once you have got very good idea about this pattern, then you can think of, if I have a microgrid, what should be the capacity now? What should be capacity in like let's say after 2 years, or what should be the capacity after 10 years? So you can plan accordingly, because we just don't want to install what will be required after 30 years, right? Because all technology, they have got a lifetime. So there is no point, something that gonna be utilized after 10 years, we're gonna be installing now, right? So you need to have a very good understanding what will be happening in that area, not only now, but also after 10, 20, 30 years. In many cases, that what happened, like Indian government might have a plan, let's say particular area, it might be coming new industry, sometime, might be new airport, and so many things might come. So you also need to talk with different, government and other people who actually does that policy. So they know in which area, what sort of infrastructure they're gonna build, right? Would there be like any like new residential, commercial home? So what I'm trying to say that you need to have very good idea before you're gonna design either hydrogen or even like a non-hydrogen based microgrid. Otherwise, something you design and after 5 years it might be not enough, and again you have to do that. So if you have those tools, that gonna help you to do that sort of study. So okay, let's just go back few slide. So again, this is sort of microgrid actually we design in that particular area. So here you can see that we do have like hydrogen, and then it has got other devices as well. But although we didn't have hydrogen market yet, but we just consider that if we have a hydrogen market, I mean, how it will gonna interact, I mean, with the local hydrogen based market. But definitely, I mean, you know, like the electricity market, we believe that when hydrogen gonna be like a cost effective, we do have hydrogen as well. Now, I'm just giving some background actually the area that I mentioned. So that is actually in Tasmania, that microgrid we designed. And why actually we designed that? Even like, you know, if you want to do that also, the question you're gonna ask that why I'm gonna doing or gonna be installing microgrid. So what happened, the area that we selected, so I'm not sure, have you heard about that SCI-D and SCI-FI? So that's a reliability index, like for a particular period, how many times or how long you are like, you know, without power. So that index will tell you like the power system reliability. Now here in Australia, there is a standard for every like, you know, power utility, they have to meet that standard. If they actually fail to meet that standard, then there will be like a penalty that you could not, you know, satisfy that particular reliability index. So here in that area, what happened, like, you know, due to bushfire and severe weather condition, in many times actually they could not, you see the dotted line, they actually could not meet that requirement. So that's one of the reason. And also as I said, that area was supplied by a transmission line which is more than 80 years old. So they don't want to, you know, build or, you know, replace that transmission line, and they asked us like, you know, what could be the solution, right? So we found out like there are like, you know, could be 5 possibility, I know, but each of them have got your, you know, their benefit and limitations. But again, I mean, I'm not gonna read or explain everything. So we try to find out the option 4 and 5, that whether we can build a like a new standalone microgrid, or we could have like, you know, hybrid option, in the sense that maybe next 5 years it will be grid connected, and after 5 years it will be like a completely off grid, because still they can use the transmission line, and they can start the microgrid now, and then they can keep continuing increasing the capacity. At certain point when the transmission line, you know, cannot be utilized, they can go for like completely hybrid. Now again, I mean, I'm also not going to talk that much detail about all this forecasting technique, because it's going to also take time. So again, I mean, for the long term forecasting technique, we forecasted for next 25 years. And what actually we take input data for the forecasting technique. So we take like, you know, percentage of different electrical device integration, like it's not only household appliances, right? So you might have different like electrical, electronics device. So we did consider like, you know, by talking with different stakeholder, that in that particular area, based on their experience. And not only that, other thing also we did have number of community consultation. We did talk with the community, like, you know, what sort of technology they want, what their preference, do they want to share energy, like, you know, with their neighbor, because unless, I mean, whatever you design at the end, it is positively taken by the community, that will not be sustainable. So that's why you see like even all country, when they do project, they do community consultation, talk with the industry, talk with, you know, other stakeholder, just to make sure that they actually take their preference, and then in your design you reflect whatever actually they are asking for. Like if your design reflect that, then it definitely that gonna be, you know, accepted by the community, and it will be like a long term sustainable. Now there are, you know, many method, but here we like here I'm showing like one deep learning based model and one is like a statistical model, just to see like how they perform. And the forecasting technique, there are many application like for planning cost of future energy. If you want to prepare for any difficult situation like a pandemic that happened, renewable energy integration planning. So there are so many applications for forecasting. Even if you want to do a good energy management system, that also need forecasting technique as well. Now here, like for forecasting, we consider like a different scenario. So for example, like a business as usual, like whatever happening now, if continue the same like way that it's happening now, business as usual, then what would be like power in the next 25 years. But what happened that if we expect like very hot weather in coming years compared to what we are experiencing now, what happened like if we feel like more severe cold weather, then how the demand gonna be look like. So we like once you do like this sort of different analysis, and from that probably at the end you might consider average of whatever the scenario you're gonna done, then we'll have a good understanding like what power requirement I will be having, let's say in 2040 or even 2045. And it's not only demand, but how the temperature might be, how would be like the rainfall, or how would be like the solar radiance, wind speed, and so on. So those are the different things we did forecasted for that particular area. And even if you want to design, you have to do the same. And then also we did like the short term forecasting. For short term forecasting also we use that mostly that LSTM, which is people use widely in the literature. Also we use like PVCNN as well. And then we use the data that actually we collected from our industry partner, but also we collected some data from ourselves as well. And again, I'm not going to discuss, because any machine learning tool you're going to use, you're going to follow this all like input data cleaning, feature selection, clustering, and then you're going to sometimes also use the hybrid, like one algorithm going to tune parameter for others even to improve the performance. And then again we did forecast as I say like 5 minutes, 15 minutes, and 30 minutes. But here I am not showing all the result. So we did for PV, wind, solar, and so on. And we have like almost like the real time system. So it will show you like exactly what you are getting and how you can what you can get actually for 5 minutes. And their algorithm also updated, like based on your previous forecasted data. Again, they're gonna take you as a like a input, and that's how the algorithm actually gonna update it, the outcome continuously, so that it's not only using the data for like what you have got 2 years back, but also you are using the updated data as well. Now once you have got good understanding about the demand profile and also what generation technology you're gonna use based on the local weather condition, then you're gonna go for microgrid design. Now again for design, you will find many algorithms available in the literature. So here, when we design, we actually consider two approaches separately, and also in the afternoon when we will do the tutorial, we're going to show that MATLAB although we use both MATLAB as well as Python, but as this course mainly use MATLAB, so we're going to show MATLAB. But we did consider two different design just to compare the cost, that if we include hydrogen, how it's affecting the overall cost of all the microgrid. Now when you design microgrid, again always you have some cost function, also you put some constant, and you also use different index to analyze the economic part as well. So here we use number of terms, NPV, ROI, payback period, levelized cost of energy. So NPV is actually net present value. This one is return on investment. This one levelized cost of energy. Because what happened, unless you can show that your project is profitable, either for investor or community, nobody gonna be interested, right? So whatever project you design, definitely it has to be technically feasible, it's gonna be stable and so on. But I think the first requirement is that that project needs to make money, otherwise nobody gonna use it. So once you have those economic index, it will give you the exact picture that whatever investment you are making, how long it might take to get return, and when it's gonna be project gonna be economically profitable. Okay. So this is one of the cost function we utilize, and here the cost you can see for it could be power to hydrogen, and then sorry, it's the investment cost, maintenance cost. Also we consider the operating cost as well. So what we do that for both capex and opex, which is again all the investment that you need. When you design, your expectation would be that you reduce the cost, but at the same time whatever constant that you're going to put, that power balance or minimum, the all the devices, they operate between their minimum and maximum capability, it has to be within that. But again all this economic factor is not that difficult. I'll leave it, and also the equation is also given how we can determine the different cost factor that you're gonna be using. Is very actually simple, almost like algebraic equation. So once you have those costing parameters, for example, if you buy photovoltaic system, what's the cost per kilowatt? If you buy wind turbine, what's the cost per kilowatt or megawatt? Same for battery, hydrogen. So once you know all the cost, it's not difficult, and once your design is finalized, how how your those all the index will look like. So some cost I'm showing from this project. So again I'm not going to repeat. So we consider all the possible option, and then we did like that initially non-hydrogen based design, what a capacity need for that microgrid, and then the total cost, and then return on investment. You see, only after 2 years actually this becomes positive. So from third year that project is gonna make money. So this is one index, but as I said, we also did total cost benefit analysis, both for non-hydrogen and hydrogen based analysis. So here it takes quite longer. That one is 2 years, but it takes 8 years just to make it even, and after that it's gonna be a profitable. So hydrogen definitely that's most an expensive option than the other technology, and we also did like different sensitivity analysis just to make sure that if something changes, still your design is robust enough to supply power for that particular community. So we changes all that defined option, and then we produce like maybe hundreds of design, and from that we found out what like the best option for that particular community. So other things also we did, we not only did the design but also economic, but also we did the control and stability part as well. And to do that actually we developed microgrid digital twin. So you might also heard that digital twin technology is getting popular in many other industry, but also in the power industry as well. So we did develop microgrid digital twin modeling in our laboratory using OpenRT and different inverter converter model. So we use both some hardware, some software, and then we develop that digital twin, because once you have digital twin, you can do whatever analysis scenario that you want to do it, because in practical cases in power system you cannot do, for example, three-phase fault studies, right? So here the good thing is that any study that happens, so this is the system that we design for that particular community. It shows like because here we found that only solar, battery and mini hydro, that's the most cost effective option, but later as they want hydrogen, we also included later hydrogen in the design as well. And then using MATLAB and OpenRT, we did develop the design and we implement it in the lab. And this all of the studies that we mentioned. We also did that grid following and grid forming that we discussed yesterday, and also we did like switching between grid following to grid forming and grid forming to vice versa, just to make sure that it has got like a smooth operation under many different operating conditions. So it's not only simulation, but also we did experiment as well. So anyway, probably I will leave it here. So although it's short, but I think now at least you have got good idea that what are the steps you need to follow if you design like either hydrogen or non-hydrogen based microgrid. But also it's not only design, but also we did develop some machine learning based algorithm for predictive maintenance as well, like constantly collecting data, analyzing the performance, and that's how you provide some early indication that which equipment might need maintenance work, so that your system not gonna be like completely out of power. So once you have got that continuous monitoring, then it's gonna be like a more resilient and reliable as well. So most of that tools actually we develop, we do have a plan to make it open source, but still we are working with the university. Once it's done, I will inform Dr. Animesh, and if any of you are interested in those areas, you can use it, because there are many software actually available in the market, but you will not find one single software that does everything together. For example, if you use Homer, that can give you like only for economic analysis, but other forecasting, the maintenance cost, and also the economic analysis part also we did. So in that microgrid we have got 30 consumer. So we select any consumer, it's gonna tell you that any part of the time how much money you are making by using the microgrid. So that also you can easily do. So that also we did in that platform as well. Thank you.
Thank you, Professor. So we'll take 5 minutes questions from audience.
Sir, in the microgrid, is there any standard microgrid test setups were available? Like suppose in AC we have IEEE based standard systems will be there. In DC, microgrid will be there?
Well, yeah, I mean, you're right that for AC, there is a standard, I mean, already available from IEEE. So, there are, I mean, some similarity between AC and DC, but there are, you know, that differences as well. So, I knew that, I mean, there was a, working committee from IEEE for developing that standard, but I'm not sure they have already, you know, finalized that standard. But I know there was a, like, ongoing working committee. They were trying to develop the standard.
So suppose, sir, I am a research scholar and I have to test some, suppose a fuel cell and integrate with the grid. So which kind of test system which I have to use and that?
Well, again, I mean, the test system, I mean, probably again, we can use any of them, but how we select test system, that's also depend our research standard, I mean, interest as well. For example, let's say, I mean, if you want to do a study on stability, right, and you are using a system which is never going to be unstable, okay, then I mean, that system will not be good for you, because the system is always, you know, highly stable, right? So you need to find a system that have a possibility to go unstable. Then, I mean, you can work on how you can make the system stable, right? So if you're what I'm trying to say that if you're interest for economic, right, then I mean, your system should be that something you're gonna choose where you have got like cheaper supply option, whatever the sources, because the power that we get is not same price from all sources, right? But if your interest more like stability, control, protection, then you have to take a system microgrid that already you know, might be having stability issue if something changes. For example, let's say when you are producing hydrogen, that actually showing some impact on the like a overall system. But having said that, it's better to start with the benchmark system. Benchmark with that already people have tested.
Available in a literature or papers work.
Yeah, many IEEE they have got, you know. For example, if you do like reliability test, reliability analysis, there is a test system that is already benchmarked. If you do like a small signal stability, there are some, you know, I mean, test system available. I think for microgrid, I know like, but I'm not sure like for exactly for hydrogen, I don't think they have mentioned that this is the benchmark test system, because, you know, hydrogen is still like, you know, evolving technology. So it might come, but, you know, but again, I mean, you can start with any like, you know, IEEE benchmark system, because that's result you're gonna give. You can have some confidence that whatever I'm getting is correct, because that's already benchmarked.
Means we can justify with our test system also, sir.
Yes.
Okay, thank you.
Sir, forecasting details what you showed, you have applied AI techniques to forecast.
Yeah, most of the forecasting, I mean, nowadays they use machine learning, deep learning. Depending, again, I mean, you know, like probably, you know, machine learning, deep learning, like depending on the data, again, how good your data, when, like, whether you're going to have supervised, unsupervised. There are so many, like, you know, technique available, and that depends on your data. Depending on the data quality, probably going to, you know, pick up which model will give the best accuracy.
Yes. That data was collected from the system what was created, or it was
no, we collected the real data. We didn't create the data.
Created, collected
because
the data.
Created data, I mean, for publishing paper is fine, but when you're going to really design and deploy the real microgrid, that's not going to be
Okay.
working. You have to collect real data.
Any more question?
So we do have pre-existing methods to generate electricity from renewable sources, from solar and wind. So we are modeling those again to improvise the pre-existing methods or new ones.
Sorry, did you hear the question correctly? I couldn't. I didn't get the exactly.
So we do have pre-existing methods, right, to generate electricity from renewable resources.
Yes.
So we are modeling those again to improvise the pre-existing ones or to find new alternatives.
Can you repeat it?
He is asking like we have already existing way of how you generate the electricity using the renewables.
That's right.
So for this analysis, are we going to change the basic principle of generation or?
No. We are not
Am
changing
I correct,
any,
right?
we are not changing any basic principle. Only things you're gonna change just to make things more energy efficient, more cost effective. How can you do that? You improve the process. You don't change the physics. Like we from sunlight we generate electricity, right, using solar. But what we are changing, that principle is same. What we are changing to have better material, right? We are trying to have better design of the the whole panel, so that with the same size we can have more output power. So if you go like few years back, probably you're gonna get like 100, 200 watt from a panel. Now we are getting 400 watt from the same size panel. So what we have changed? We have changed the material, we have changed the process so that it can capture more energy. So same for wind. Like we are having better technology just so that we can capture more energy from the system. So we are updating the method, but principle remains same. And sorry, I was having problem to understand the question. Sorry.
Sir, I have a question with respect to yesterday's session.
Mm-hmm.
The short circuit ratio has to be checked at the point of common coupling when we are in this stages of deploying the microgrid, the stages. Where does it stand among all the tool development stages? Also, when we are having the microgrid point of common coupling with the grid, so the short circuit ratio is same, it has to be equals to less than or greater than 3 in this case also.
Yeah, again, it should be the same idea. Because again, if you have that very short circuit ratio very low, and if you connect microgrid, it would be, quite challenging. It's not impossible, but again, probably, you have to go for, either other additional devices, depending on the problem that you might be having. Yeah, or you need better control that, many of that we mentioned. But again, that is true for, either only the normal grid or microgrid when it connected with the main grid.
So sir, among this, which stage involves that short-term focus team? Those stages are forecasting. After that, in the checking stage, microgrid design tool, or where are we checking that short circuit ratio?
Short circuit ratio, definitely, you're gonna check, when you're gonna thinking connected with the main grid. At that stage, you have to check it. Because that will come when you're gonna connect with the main grid. So that time probably, the point you'll be thinking. But again, having said that, it's not that we're gonna check at the very last moment, because when you're gonna design, also in the design you will have that, at that point, we're gonna be connecting with the main grid, right? So it's better even to check even in the planning stage.
We'll take, we are running late, so you have a short question? Okay.
No, you can continue, no problem.
Hello. Sir, one out of curiosity, you have done this, you got the simulation results before means when modeling of simulation results, real-time results by using Opal RT, and then later you implemented this grid, isn't it? So what are the technical challenges you experienced during the implementation? Because simulation results and then actual implementation, probably
Yeah, I mean,
you may having the different problems.
So the implementation definitely have got many challenges. I mean, so you are asking mostly technical challenge, right? Because there could be like so many other challenges, but that's not our job. So the technical challenges, I mean, again, I mean, one of them that when you have that, definitely do the simulation for control and energy management system. So whatever parameter you think that providing the best performance in the simulation in experiment, in many cases it doesn't. So in many cases, I mean, you have to again, I mean, retune and then and set all the control, I mean, to get your desired results. So mainly those control perspective and then energy management. So that was like the thing that was heavily differentiated from the result that we got from simulation. But again, I mean, all the simulation, I mean, you do also different, as I say, like sensitivity analysis as well, that if something changes within that range, still, I mean, your design is valid. So that's gonna give you less like technical challenges when you're gonna go for, I mean, real implementation. But definitely, I mean, it's gonna be having challenges.
Okay, so we'll have 5 minutes break. We'll start the lecture 11.
Hmm? Yeah. Sometime it takes some time. Oh no.
Can you cancel?
There's having problem from this.
Protection as expired. Huh?
Why? I don't know. Okay.
Why that is not going?
No, it will. I don't know. Voice finding security risk.
Can I close? What? No, this is from Office Security. By opening some PPT file. So can you again open the form?
Okay, let me just check.
Can you make it PDF?
Why? Why is having that problem? I couldn't understand.
Yeah, PDF you save, no?
Yes.
Again open the PDF. Minimize it. PDF is saved. And no, you open the PDF, you minimize.
No, but you have to delete. You cannot
close
minimize
it.
unless you finish this one. You cannot do it anything.
Control Alt. Delete.
The task manager is not doing anything.
Just click here and task Microsoft PowerPoint.
What is doing?
Close.
How you can make it?
Presentation.
Yeah.
Why did not share? This one, Windows P. You have to slide like. We can put it in presentation mode. No, but there is something. Oh. Now you can go.
Okay. Is it only one page?
No, 43 page.
Yes, so why?
Initial page is not coming anyway. So you start from this page and
Okay.
and then from where you see.
Many things.
We are running 35 minutes late, so I'll keep my talk half an hour.
No, this one also would be short.
After this, we'll have tea break. Then I'll have the. Try manage 30 minutes. I'll finish.
And I will also this one will be short, not that long. Because not much difference between these two, right?
The initial 15 minutes we got left for this project.
Yeah.
Okay, welcome back. We are starting now the lecture 11, which is about the control and operation of wind energy power hydrogen systems, and will be talked by Professor Jahangir. Over to you, Professor.
Thank you, and again welcome back. So again, I mean, the microgrid that we discussed is not like any significant difference, like when you have only a hydrogen and green hydrogen system. So it's quite similar. Only things, I mean, what is happening like here, that the green hydrogen system use output power from wind, either to produce hydrogen, or again convert hydrogen to electricity. But other than that, I mean, there are not any like a significant difference. So what I'm going to do here, I'm going to go like some discussion on the wind energy system, because we already have talked about hydrogen, and then I'm going to show like one example that when you have got hydrogen wind system, how we can model it, and also the control technique that we discussed previously, how we can apply and check their performance. But in terms of like overall technique, there are not that much significant difference. So as you know that, I mean, although we are talking about both solar and wind, but in many cases in many countries, like wind power actually dominate over solar. And the reason is that, from a single wind turbine, do you have any idea like what sort of output power we can get from like a big size wind turbine? Like 15-16 megawatt, like 16 megawatt wind turbine is currently available. And you see, if you want to get even like 10 megawatt output power from solar, how big or how many houses you need, right? You need plenty of space. So that's one of the reasons, like in any country where the space and location is a problem, then definitely, I mean, wind farm, that could be a better choice. But having said that, I mean, for community microgrid, community don't like, in many cases, many community don't like wind farm, because they say like it produces noise and so on for environmental reason. But that actually problem also has been addressed. Now if you have like a new wind farm, their noise level even less than whatever pump we normally use for water or agriculture. So noise actually is not any more issue. Another thing, I mean, many countries like even in Australia, now they are planning for number of offshore wind farm. So all the like space that we have like in the water, like sea and things like that. So you put wind turbine over there, you're not using any like usable space. So only thing you just need to build transmission line, which again, I mean, as I mentioned, that people going more like high voltage DC. So that's the only things you need. So in Australia, that they have already actually planned number of new offshore wind farm, and not only of Australia, like in Germany, Denmark, they're also having like number of new wind farm as well. So again, I mean, as I said, like if you have wind powered hydrogen microgrid, it would be that initially we are generating electricity from wind, and then you convert either excess energy or even like whatever it could be complete energy as well, into hydrogen via electrolysis, and then you can store energy, and then again, I mean, you can convert hydrogen back to electricity if needed. So that's like same thing that we discussed previously. So these are the main component you need. So you need like wind turbine, electrolyzer, hydrogen storage, fuel cell, or even like engine, which also can be utilized to produce electricity from hydrogen, and then different power electronics, inverter, converter that we mentioned, and then we need a microgrid controller as well. Like other application, yeah, it could be also having like similar application for remote community, like village, island, defense microgrid, industrial site. It could be for agriculture operation, like ports, mining, those sort of area. I mean, we can think of like hydrogen and wind powered microgrid. The challenges, some of them we already talked many times, like the cost, efficiency, hydrogen safety, and then I mean integrating multiple technology, the control optimization for real energy management system, and definitely like solar, we also have like wind variability as well. So that's again could be either battery or the other option is the hydrogen, which we are talking about now. So if you have got a hydrogen based microgrid, definitely I mean it would be long duration storage, not like the battery. Battery would be like a few hours, but here you would have like days, even like for month. So that's like a big advantages. It ideal for like remote islanded system, because if you go most of the cases islanded area, you will get like a good flow of wind, where you will get enough wind speed. So in that cases also this microgrid would be a good solution for remote and islanded system. Like others, that also can be contributing to decarbonizing the country or area. Definitely for like other microgrid, it can be also improve energy security, continuity, and also like for sector coupling. So hydrogen can be used for transport, heating, industry, not just for the electricity. So the multiple sector can be connected together as well. So again here in the beginning I will go quickly. So wind power is like it's not like the fast application to produce electricity from wind. You know that people use wind for windmill for many decades back, to produce mechanical energy for other application. For example, let's say water pumping, sails to propel ships. So we use wind energy, but that was for other application. But recently the electricity from wind power is actually getting quite popular. So as I mentioned, like the currently so the biggest capacity available in the market like 16 megawatt, and you see the rotor diameter is like 242 meters. Mainly it used for like an offshore wind farm, because that's quite very big, and it can generate up to like 80,000 megawatt hour of electricity annually, which can be utilized to power 20,000 homes. So you see like only one single wind farm, how many homes actually can be supplied. So that's one of the reason, as I said, like for 100% renewables or close to 100%, solar is almost like impossible. So we need wind and we need hydro and other option. So now it's 16, you never know, like it might go like 20 or more than 20 in coming years. So you might already have some knowledge about wind. So you have like the blade, and then that you have got turbine, generator, control system. Also normally from wind you find the output voltage like close to 700, 690, 700. So you also need a transformer when you're going to connect with the main grid. Each of them have got their own function. So yeah, again from wind, the blade or the turbine that going to capture the energy converting from wind to mechanical, and once it rotates, definitely there is a gearbox, because that the speed of the wind is significantly lower than the speed of the generator, right? So the generator speed much higher than the wind speed. So we need like a gearbox in between, same thing like a transformer. So you know the transformer for stepping up voltage from primary to secondary. So this is also like the 2 speed. So we need a gearbox as well. How we can model is very simple equation. You know that kinetic energy equation half mv square, right? From there you can easily develop whatever the power you're gonna get. So this like that area that you're gonna capture for the wind for the turbine. So if you consider that area A, where the air density rho, which is fixed, has got fixed value, so which has got that fixed value rho, then if you put it and converting like mass in terms of volume, then you're gonna get this equation. So for any wind farm, you can use the same equation, and you can see like for considering the diameter, area, that wind speed, what sort of power you can get for a particular. So it's just like giving one example that 20 meter per second wind speed, blade rate 30 meter, what wind power you can get. But that's again like this is the input power, not like the output power. So this is the input power. You're gonna get it just converting from this one to area, and then if you use the simple equation, you can see this sort of power you're gonna get. So if you really want to design wind turbine, then this sort of modeling is needed. But for just doing simulation, I mean, you don't need that. So with diameter, there is a like significant changes, whatever the output power you're gonna get, and that can be done from previous equation. And you can see that with the diameter, the relation, I mean, is when you calculate the area, is relation is E square, right? So with the radius, the relation is E square. What I'm trying to say that, I mean, if you just double the diameter, your power gonna be reduced by 4 times, because the relation is E square. And then whatever the input power is coming, to get the output power, actually you need to multiply this another coefficient, which is called like the power coefficient. And this power coefficient has got like a maximum value, because so far from the wind we can capture maximum 59% energy. You never would be go beyond that. I mean, whatever the technology available, you cannot capture 100% energy from the available wind. So this is like the theoretical value, 59.3%, but normally all the practical wind farm you can see, it would be around like 40%. So let's say in the input, if you have got 100 kilowatt, you're gonna get maximum 40 kilowatt as a output in the wind farm. So that thing also you need to consider when you're gonna design the microgrid and see what sort of power you're gonna get from the wind. So it's not like the wind speed and then you use that equation, you say like this is the power I'm getting. No, I mean you have to consider the limitation from the output power that you're gonna get from the wind turbine. And also like with the wind speed, the relation is cube. Like if you see that equation is cube, right? So if wind speed changes, the power output actually changes significantly. So if it is wind speed get double, the power output will gonna be increased by 8 times, right? So that's why the variation of the wind changes the output power significantly. Now, this one just showing the simplification, that if you just get the idea, like for particular wind farm, what should be the diameter? I mean, that's given like very simple equation. So, for example, if you get like 10 megawatt wind farm, you need the diameter around 150, which is the one that used in Norway is like 144 meters. So, because here we are making some assumption just to simplify that equation, but what I am trying to say that based on the power, you can have a good idea about what with the diameter. Now, when I talked about that wind power modeling, I talked about this 3, 4 speed. Now, what is that? Actually, better would be, I mean, if you see here. So, initially, if your speed is less than 3.54 meter per second, you will not get any output power from the wind farm, wind turbine. So, it has to be more than that value. So, once it goes like more than 3.54, which is called like cut-in, then you're gonna get some output power, right? But when it is reaches like around 12, 14, you're gonna get rated output power from the wind farm. But it's not that if keep continue, you're gonna get more power, because it has got the rated. After rated, whatever speed, you're gonna get constant output power. But you know that for safety purpose, there is a speed. I mean, you cannot rotate more than that due to the mechanical safety and so on. So, what happened, like all the wind farm, they have got sensor and protection. So, when there is a wind gust, like a tornado, they sense the wind and then they automatically shut down. So, that speed is like around 25. So, if you go more than that, then the wind turbine will be like automatically shut down. Now, how actually you can model the wind farm? That's our interest when you're gonna model hydrogen wind farm with the other technology. Now, again, these are the as I already mentioned, that from wind, the wind turbine capture energy, mechanical, is connected with the generator through the gearbox, and then we have got the generator which produces electrical power, and then depending on which technology used, because there are also many wind farm available in the market. Now, depending on that, it depending on like what sort of power electronics inverter converter we are using, then we have to model that one, and finally it's going to be connecting with the electricity grid. So, when you are modeling, you have to model turbine, you have to model the gearbox, you have to model the generator, and then you have to model the inverter converter as well when you're doing the whole simulation. Okay, but for only planning purpose, you just do that simple power equation I mentioned. But for doing like non-linear simulation, you have to model each and every component of the whole energy conversion system. It's not only turbine, but the whole system that you need to model. So, this is one of the terminology you will see many cases when you study wind farm or wind technology, which is called actually TP speed ratio, but this is actually given the TP speed of the blade and the wind speed, and that ratio is actually given, and in many of the model they use with that terminology. So, better you also need that. This is nothing but just the ratio between the the two speed. And then depending on the construction, it could be either horizontal, vertical, depending how it rotates. So, if you want to have a small size wind turbine, then it would be like a vertical one. It could be having in your even rooftop or in the community area, even it could be in the campus, because it's small, but it has got different types of shape as well. Some of the shape even you will not understand this is a wind farm. It looks like a toy, so it's rotating, it looks quite fancy, but at the same time it produces electricity as well. But most of the commercial one, that gonna be like a horizontal, so it's rotate like horizontally, and it has got bigger capacity. This one most of the cases would be the kilowatt range, but this is like the megawatt range. Yeah, so now in terms of the generator, wind farm mainly use asynchronous. The normal machine, I mean normal generator we use in the power system, they use synchronous, but the wind farm normally use asynchronous, but there is the next generation wind farm, they are also planning to use synchronous generator, mainly permanent magnet synchronous generator. But here I mean mostly they use asynchronous, and asynchronous is that it could be either squirrel case or wound rotor types of machine. Again, I mean I'm not gonna go very detailed, probably might know, or if any of you don't know, if you want to model wind farm, you need to have some idea about both, I mean asynchronous as well as synchronous machine. And synchronous, again it could be like a permanent magnet, or it could be like a electromagnet as well. And each of them have got their advantages, disadvantages, but for wind farm, the next generation one, they are actually thinking of permanent magnet. So in terms of wind technology, there are like 4 technology types of technology available. So this is the first generation wind farm, which is called almost like a constant speed. Then we did have limited variable speed. Now this is the 3rd generation one. You will find most of the commercial microgrid, wind farm, wind technology, that's the variable speed with partial scale frequency converter, which is also called DFIG, doubly fed induction generator. And then the 4th one, which is more like R&D level, but that might be coming soon, and like in the commercial level as well. So that's like a full control. So the 3rd generation one, you have got partial control, but the 4th generation one, you will have like 100% control for both active and reactive power. And this one is showing the constant speed wind farm, wind turbine. And here you can say that this is quite similar, like the initially we have got turbine, gearbox, then the generator, which is squirrel cage induction generator. Now why actually we are using that capacitor? Because this is the additional component. This is not the part of the wind turbine. Because squirrel cage induction generator, it consumes reactive power from the system. So it has got like negative impact on the voltage. So that's why, I mean, to control the voltage or to improve the power factor, we use the shunt capacitor. So this is quite compulsory. If you use this turbine, it has to be some additional compensating device with the turbine. And then we also use like a soft starter, and also this is that during the starting periods, this type of induction machine, they take high current from the system. So to limit that initial current, what we do, we are like this switch is like open, so there is like additional resistor in series with the turbine. So that means this is limiting current coming from the grid. But once it is spin and rotate close to the rated speed, it produces the back EMF. That time current automatically reduce. So we don't need that additional resistance, because it's gonna be having some losses because this is resistance. So that time it bypass. So this only use at the starting period, beginning. Good thing, this is inexpensive. The technology is massive, but the problem is that we need additional compensating device to control the voltage. So this is the next generation one. It's not like squirrel cage. Squirrel cage, as you know that the rotor is internally shorted, but for squirrel cage, the rotor is connected with the additional resistance box, which can be utilized to control the speed, but the control range is quite limited, that's why it's called limiter. And this is resistance box, so there will be like a power losses as well. So again, I mean, that's why people are not interested for this type as well. So this is the most popular one, and many of the modeling you will see that people in the literature they use this one doubly fatty induction generator, which is also called like partial power electronic converter. Why we call it partial? Because here like almost 70% power from the wind goes directly to the grid, not via power electric converter. So through this converter we have only 25 to 30% of the power actually transfer this path. So why we do that? Because in that case, for example, if say your wind farm is wind turbine is 10 megawatt, then you need 10 multiplied 0.3. So inverter converter capacity will be only 3 megawatt, right? Because the inverter converter quite expensive, is very sensitive. If there is a disturbance, there is a possibility that it can damage. So that's the reason we only use like 20 or 25% capacity. But still, I mean, you don't have control over 100%, but still you have control over 20 to 30%. So still that good enough to control, provide both frequency and voltage control function. Again, I mean, for controlling purpose, I've just given like, I mean, for gearbox also, like there are different types of model available, third order, fifth order. So many people use this first three equation to model that gearbox, and then like your generator, both rotor side, stator side, and then for this rotor side converter, grid side converter, also you need, I mean, different control here as well. So in terms of control, what sort of control we need actually here? Mainly three types of control. One is for here for like the turbine, they use like the pitch control, and then for this rotor side converter we need one control, for grid side converter we need another control. So once like you have that model, and then I mean depending on what sort of control and what other devices, then you can go for designing control. But this is the next generation one wind farm, where you can see that your both rotor, I mean 100% power gonna be going to the grid through this converter inverter. But definitely you will have 100% control, but thing is that the inverter converter will be very, very expensive, because that whatever capacity of the inverter converter, that has to match with the generator. So if it is for example 10 megawatt, that also has to be 10 megawatt, which is at the end improve the performance, but it would be quite costly option. So this is like one example of wind, hydrogen, you can say microgrid, or just like a could be with the grid connected as well. So here you can see that we have got two wind turbine. So as I mentioned like that, we need like a one piece controller to control like the piece depending on the like wind variation or wind direction. Sometimes we sense like the piece just to make sure that you capture maximum energy available from the wind. And sometimes also like if you have got very high wind, also I mean that helps, I mean even to slightly bit for the protection purpose as well. And then you have got this both like generator side and the grid side. So this is like the generator side controller, this is like the grid side controller. Now this both controller has got different function. So the one of the controller, they mostly control the DC voltage, and another controller they control the active and reactive power. And then this output of the turbine is going to be connected with your electrolyzer through this again, AC to DC and DC to DC converter. You could also have, electrolyzer here, but we haven't done electrolyzer, but it could be done whatever, like the hydrogen, you could have another electrolyzer and connect with the system as well. And then you have got like two types of load. One is resistive, another like a capacitive load. So, and then you can actually do that modeling if you want, like working in this sort of configuration, and then you can do the simulation. Now, I already mentioned like that for piece control, what actually we need with this, we need that speed input, the rotational speed, and then depending on the reference, it's gonna be producing the piece angle. But you know that normally there is like a maximum and minimum limit that we set. So we set normally just to avoid the mechanical stress, we limited like plus minus 10. So we control it, but it has to be like within limit. So you put that limit, maximum and minimum. And then the generator side converter, which main purpose to maintain the DC voltage. So here you see that the DC voltage input, from that it produces the reference current, and finally from that you're gonna apply in your converter. But here what will happen that like that when there is a change, like the power demand, for example, let's say when your power demand rise, what going to happen? For the DC voltage, there is a balance between DC power and AC power. So if one of them increases, so what will happening? You will find some changes, and based on that changes, it's gonna be producing the different reference that it's giving to the converter, and that will give you like to either to deliver more power to the grid, just to make sure that your DC voltage is constant. So based on that, either your load increase or load decrease, it's gonna produce the control action just to make sure that constant. So the other side, the grid side, this is more like reactive power, and speed, that's like also for real power as well. So that's gonna be giving by your this control. Some of them also use like this MPPT concept here as well, depending on like whatever mechanical power we are getting. We can get like corresponding speed that gonna giving you like the maximum output power. And then you have got the grid side converter, which is again as I say like mostly controlling the voltage because it's connected with the grid. And then you also have the electrolyzer control. Again, this is like a very simple control just to maintain the voltage using the PI. And then here the simulation shows with the different wind speed. So initially this wind farm was, one of them was like a like off, and then only one of them was on, and with this input power was coming as an input to the electrolyzer, and then when that speed changes, how both of them is behaving, and then at some stage the second one is also turned on, and when both of them have on, how they are behaving, and also like how the frequency also changing with respect to those wind changes in the system. So just to do like showing your stability, you can change those different parameters, and then you can see like how the system behaves. So As I say, like, you know, in Australia already we have like one, then like in the operation in, I think in Western Australia. So they already have hydrogen and solar and also some wind in the system. So like previously, I mean, I also given like, you know, some of the idea that probably you can think of if you want to work, you know, hydrogen and wind. Sometime it could be that both hydrogen, wind plus PV. So these are the some of the area people are still thinking to do more work because they still need further work. So yeah, so these are the things probably, you know, I'll leave it to read at your, I mean, either now or, you know, later if you really want to work in that area. Thank you.
Thank you, Professor. We'll have 5 minutes question. Any question? Yeah.
Professor, you said the maximum efficiency in capturing wind power was 59.3%.
Yeah, that's the conversion. That's not the efficiency of the wind turbine.
Of capturing the wind power.
That's
That is
the maximum you can capture.
Yeah, that is an empirical value, or is it derived mathematically?
That is like there is a, like, you know, equation that you can solve. That's from that, you know, using that defined parameter that actually give the theoretical value. I mean, by modeling, from modeling, like, because in reality, I mean, like when actually it captured, so they found that, I mean, through even like they have also proved through experiment, actually they cannot go beyond that value. So that has been done theoretically, but also, I mean, practically, as I mentioned, like when you really deploy, you're gonna get maximum around 40%.
Thank you.
Okay, so we'll have a high tea break now. So tea is arranged in the next room. We'll have 10 to 15 minutes break, then we'll start the next session.
Can I?
You will find EV load also. So that is a good one. That's what I'm saying. You see first. No, that is, I have seen that model is there, but I have not done voltage stability. You can use that and do the stability analysis. Significant renewable energy we can use to produce the electricity, which is wind energy, right? Then when you say renewables after wind, what it comes to our mind also solar PV, right? Now again, before I start, I'll ask one question. So what is the solar PV output and what is the input for electrolyzer? DC, right? And so, but in wind, what you saw, like you generate AC and then you have this extra rectifier stage to bring down the AC generation to DC, right? And again also here also I can say it can operate in both mode. Let's say you are only focusing on DC grid or DC microgrid. There you may not be need because all your generation and loads will be DC, okay? But some application, let's say you have a big solar power plant where you are going to use some hydrogen electrolyzer in the existing solar power plant in the megawatt scale, and the solar power plant is already connected to AC grid, and in a common bus you want to connect a hydrogen electrolyzer load. So that time you might need a rectification stage because you are bringing the power from the AC grid, okay? So in this talk that we are going to discuss. So I'll discuss a brief of introduction and a overall system architecture, okay, how a solar PV power fed electrolysis can happen. Then topologies, what are the topologies? When I say topology, maybe I am mostly talking about the power electronic topology, what can be involved in those process, solar PV power fed electrolysis. Then MPPT control method, as all of you know, I know, but I will just give a brief, like some people asked in the previous session how this MPPT is a theoretical or mathematical. So what are the processes involved and why it is called maximum power point tracking? It applicable to both solar and wind, and in solar perspective I will discuss here. Apart from that, as we told, it is a DC grid or whether you are taking from AC grids, because hydrogen electrolyzer yesterday and from beginning we know it is a low voltage high current device. So whatever DC you generate, sometimes depending upon the architecture you are going to use in the process, you might need some kind of DC-DC stage in between, whether it is a DC-DC boost for the solar PV generation or might be a DC-DC buck at the end side for the electrolyzer, hydrogen electrolyzer, okay? And if time permits, I will tell about two types of case studies. where I will consider how you can do some kind of system level analysis when you have solar PV and hydrogen electrolyzer in the system. Okay. So, this is one of the again statistics. So, you can see the globally hydrogen consumption rate. It is of course till 2020. You can get the information from the given references. So, the radius of the circle tells you how much is the magnitude of the amount of hydrogen is being consumed in the different country of the globe. Okay. So, the more the radius, more is the consumption. That is how it is represented here. So, if you see, China is the highest consumer for the hydrogen electrolyzer globally, and this list is till this the data or the statistics is till 2020. So, if you want to know updated thing, you can search, but this is collected from the source I mentioned. So, that means by 2020 itself, all over the globe people are aware of this hydrogen electrolyzer consumption. That means, and now to consume something you need to generate hydrogen first, and that is why we are coming up with whether different types of hydrogen production, which already we discussed. So, one of the technique is green hydrogen, where we use some kind of renewables, whether is wind or solar, to generate this hydrogen production. So, now as I told, our India also itself is targeting almost 500 gigawatt of non-fossil fuel based power generation by 2030. So, to accommodate all huge amount of renewable energy source, also India has a mission called National Hydrogen Mission. In that, they are also targeting to generate more and more hydrogen by 2030. So, that because it is a storage like battery. So, once you have a more renewables, you can definitely predict the power generation profile will be very much fluctuant. If you remember some of the previous slides of Professor Jahangir, once you have more renewables, your power demand and the generation profile itself not very smooth. And to mitigate that, we have a concept called demand flexibility, where mostly battery we use, but in upcoming generation we are going to use hydrogen energy storage. So, to accommodate more and more energy, renewable energy, we are coming up with more and more hydrogen, and all not only us, all over the globe you can see it is almost fair distribution of consumption. Okay. Now, why we require PV based green power, green hydrogen? Because it is the first global push of carbon neutrality. It is a very generic statement. I mean, it is not only applicable to solar PV, it is applicable to all kind of green energy which does not emit any kind of greenhouse gases, right. And then from that we also know that this hydrogen is a clean and storable energy sector, and PV driven technology, of course, as solar PV is involved and you do not emit any kind of greenhouse gas, and also it is scalable. You can have a solar PV power fed electrolyzer at a distributed level, which you can call microgrid level, and when you talk about the grid scale hydrogen integration also, there also you will have other resources. So, you can build megawatt scale level, and of course, when you go for that megawatt scale level and connect to grid, definitely you can help in some kind of grid ancillary services. So, that is why that becomes a scalable technology. It is scalable from the kilowatt level to megawatt power level. Okay. Depending on application, you can use that. I am doing this. Again, this is a sketch of the solar irradiance distribution, and if you see, the scale is basically a radiation curve, a radiation scale. And if you can see, based on the geographical location where we get the more and more solar irradiation. Okay. And mostly if you see, it is more and more red. So, the radiation I mean measured in terms of kilowatt hour per meter square is more. Okay. So, here I can see mostly some part of Australia. If you see, this is the Australia and some part of Africa. You have the high radiation, and the lowest radiation you find mostly in the American region. Okay. So, what we can do here? So, basically we integrate the electrical and electromechanical electrochemical subsystem, right? Because solar again energy it produces electrical energy, but the consumption from the load perspective, load is basically electrochemical load, right? What we discussed, the electrochemical equivalent. So depending upon that, so it basically combines that electrical energy to produce some electrochemical load, and also you have to properly model it to get high efficiency. Okay, so you are getting solar irradiation and generating solar power, but your power transfer to the electrolyzer should be highly efficient, whether you are using through AC to DC stages, multiple DC-DC conversion, or you are using directly solar coupled DC-DC. So that converters or the total solar hydrogen electrolyzer membrane, all these things should be properly designed, so that when you whatever the generated energy should be highly efficient when it reaches to the hydrogen production, so that your hydrogen production will be also good. Then we will see, as I told, overall system architecture. So here I am showing a solar PV power fed electrolyzer model, and in that what are the parts involved in the first solar PV model. Okay. As you know, two factors generally mostly affect the solar power generation. One is irradiance and the ambient temperature. Okay. So those two are the most governing parameter how your solar power generation profile looks like, and that depends on electrical power also, of course. Then again, when I say solar, if it is a kilowatt level or megawatt level, it is not a single solar PV panel. You will have so many PV panel. Like we discussed, for electrolyzer, it is not a single cell that can give you the required amount of power. So single cell, if you see VI characteristics, the cell voltage is very low in the top form of 1.9 to 2.2 volt. But you have to again make it series connection and to make it a low voltage and high current device. Similarly, solar PV panel, depending upon how much power and how much particularly voltage and how much current you want at the output. Similarly, panels can be arranged in series, parallel, or both series and parallel combination, or you can also arrange these solar panels, solar inverters as centralized or central inverter or string inverter you can use. So depending upon you want to generate centralized solar or distributed solar. Okay. Now as you know, solar power output is basically a DC, right? And the DC-DC converter model here I showed. Sometimes depending upon if you want to, sometimes for grid connection of solar you need a boost converter, because the solar voltage output voltage that you generate from the DC exactly from the solar PV panel is not compatible with the grid scale DC link voltage. So you need a step up operation. So you basic structure is a single stage boost converter you can use, and you can achieve the same achieve the voltage whatever the input from the solar, and the output will be a grid level inverter DC link voltage thing. Okay. And here again what I am saying, sometimes in the next slide I will tell there are different types of architectures for this solar PV power fed electrolyzer, but in this what I mean to say, in case you are using a DC-DC buck converter, so if your solar voltage is already sufficient, you don't need, but if your solar output voltage is not sufficient, maybe you have some kind of DC-DC boost, or maybe if you want to reduce to the electrolyzer level voltage, you make it a DC-DC buck converter. Okay. And in that already we discussed DC-DC converters objective when you go for converter design or controller design. So these are the objectives, mostly the conversion ratio. We require a high voltage conversion, because if you are generating a high DC but the electrolyzer needs a low voltage DC, you have a you should design a converter that can step down the voltage with a high conversion ratio. Then also you have to properly design a controller, what I told, that controller will take care of your current ripple that can be found at the output of your DC-DC converter, because that high if you supply high amount of ripple current to the hydrogen production, then it will be less efficient. So, the controller objective also should be properly taken care of. Okay. And apart from that, efficiency. So, basically current ripple also somehow related to your efficiency, because if your input power to the DC-DC buck converter is not properly transferred to the electrolyzer input, then the efficiency will not be good and your hydrogen production will be not up to the required amount. Okay. Because hydrogen production, it totally depends how much power or volt current you are giving to the electrolyzer. You saw the electrical equivalent, the current decides all the kinds of over potential, right. If that current does not go to the electrolyzer proper amount, all the over potential will be less and your hydrogen power, output power or hydrogen production in terms of whatever quantity you use, that you may not get. So, the power supply should be proper. And electrolyzer model also I discussed everything. So, mostly different types of equivalent circuit we discussed, so we can use here also. Static model, dynamic, electrical with considering sometimes concentration over potential or avoid it, or sometimes electrochemical model where you try to emulate all the chemical reaction in terms of electrical equivalent and then model it. And yeah, so there are other models also there, thermodynamic model and all. So, this is basically a structure where you generate the solar from the solar power from the solar energy, solar PV, and then you fed directly to the electrolysis. Okay. There is no grid concern here. So, this is a very generic architecture. So, this is actually I will refer a very good paper. So, it will give you a very good brush up of knowledge about the solar PV power fed hydrogen electrolyzer. Okay. Now, this is, I think most of you know and some of you may not know. So, this is how we model a photovoltaic model, right, solar PV model. So, how many are acquainted with this equivalent circuit? Backside students, are you seeing first time, right? Okay. So, there are other equivalent models out there, but this is a very simple model to understand. So, if you see there are different current and resistances I mentioned here in term to represent a equivalent photovoltaic model. Okay. And the IL, what is coming from the source, that I called as a photo current. So, basically solar cells, what they do, they absorb the radiation and convert into electrical energy. So, that photo current IL I represent, and there is a parallel diode, current diode is also there. So, you know the current through the diode is not linear, right. So, that diode current expression is provided in equation number 2. So, it is basically exponential function and depends on several factors, and there is a shunt resistance and there is a series resistance. Okay. So, series resistance is basically a representation of the ohmic losses, the ohmic losses or contact losses that is involved in the solar PV panel. Okay. And the RSH, that is the shunt resistance, that is also a representation of the leakage current that pass through the solar PV panel. Okay. And the ISH is the that leakage current. Okay. To represent the leakage current through that solar PV panel, we represent it as in terms of parallel branch. Okay. So, all of you know Kirchhoff's current law, right? Kirchhoff's, so Kirchhoff's current law. So, equation 1 satisfies the Kirchhoff current law, right? So, your output current IPV becomes IL minus ID minus ISH. Okay. And that ID expression is given here. So, that is the output current IPV what you get. Now, if you want to know the shunt leakage current, that you can model it as a V plus IRS by RSH. Okay. And that photocurrent expression also is temperature dependent. Okay. Because as I told, temperature and irradiation. So, G is the irradiation parameter and the temperature you see Tc minus Tc reference. Okay. And Kf is the short circuit current temperature coefficient, okay, and ISC is the short circuit current. So, that photocurrent, if you see, that is what I say when a solar PV solar cells PV cells receive the irradiation and the temperature, that will affect how much photocurrent you generate. Okay. Then the open circuit voltage also is a parameter or is a function of both temperature and irradiance, and you can represent it as B open circuit. So, STC is at the standard temperature condition. Okay. So, VOC STC plus VT ln G by GST. So, wherever you see STC, that is the value at the standard temperature condition. Okay. So, now again the how to evaluate the efficiency of PV module. So, whatever the power you are getting at the output divided by the radiance and the area of the panel. Okay. So, that means whatever power you are getting or the energy you are getting from the solar, you may not get directly as the output. So, it depends on many factors as I mentioned, and that is how you calculate the efficiency. Okay. So, this is very brief of a analysis of that equivalent circuit of a solar PV model. Got it? So, basically we represent it as a current source. When you go for power electronics and do some kind of system level studies, so this solar cell we call it as a current source. Okay. And mostly if you remember, when you have a solar PV inverter, we model the controller as a grid following basically classically, so that whatever the grid wants, you just inject that current, you do not care of the voltage. So, you just follow the voltage and you inject the amount of current, or in if I say in terms of power, the active power. Okay. So, mostly it generates the active power, right. So, that is what I gave an example. In that case, somebody wants to model it, circuit model of a solar grid connected solar PV panel, you can use this model. Okay. And the topology wise, as I told, you can have several combinations depending upon which application you are using. Okay. You can even directly couple the PV, solar PV with the electrolyzer without help of converter. So, that is one of the trending topic nowadays, how to avoid converter for this application, because as I told, hydrogen electrolyzer is a high cost concern involved in that, right. So, in that again, if you add power electronic converter for even low power scale, then it does not make sense, your investment cost and the performance you want or you want to give. So, that is why in certain application where your power is not that much high or significant requirement is there, you can simply localized way you can generate direct coupling. And if you see it, as I told, it is simple and cost effective. And of course, here I will tell about MPPT. So, solar power is mostly operates in the mode of called MPPT. MPPT is called maximum power point tracking. Okay. So, what we do, I showed you the current and voltage expression of the solar PV in my previous equations, right. So, if you draw a curve between VPV, IPV, but particularly they call it open circuit voltage and short circuit current, and then you draw also the output power what you saw, which is generated from the solar PV. So, the power that is generated from the solar PV, and you try to plot that against the open circuit voltage, you will see the curve starts from 0, goes to a maximum point and then falls to the again 0 power. So, in very classical way, nowadays several modifications are there, because you do not want your solar PV to operate always maximum power point tracking, but the classical way you always try, because as I told, it increases and then falls. So, there is a peak point, right. So, the peak point means that peak point refers to the maximum power, the y axis is power and the x axis is voltage. So, that peak point corresponds to the maximum power, and the voltage that voltage you want to always maintain, because the moment you change the voltage here and there, the power point tracking will drop, so that you will not get enough output power. Okay. So that's why how people do that. There are different methods I will tell in the next slide. So either you directly control them, or you control through some kind of DC-DC interface after the output of the solar PV. So maybe what I told, like if my solar MPPT curve I want to maintain, I want to basically maintain a voltage, right? So that voltage I want to control, and that through that control I want to switch some DC-DC boost converter. That's what you can do. So anytime voltage try to go down, you try to make it up. For that, current will be automatically adjusted, so that you maintain your MPPT point. Okay, that is one way, or there are other methods are there where you can also use. That is directly coupling, but again DC coupled system. Okay, DC coupled system, from the name you know, you don't need any kind of AC conversion, AC to DC conversion. So as I told, second point already I told. So incorporate DC-DC converter to enable MPPT. Okay. So the DC-DC converter, if you remember yesterday, we are trying to control. Of course, it is for electrolyzer, but we are trying. I showed you how to control the output voltage of a DC-DC converter, right? So same DC-DC converter, the reference you are giving, you remember that reference 262, whatever some application I told. That reference you can put that voltage corresponds to the MPPT point. So anytime you change your system condition, it will try to track that reference voltage. If you can achieve that reference voltage, at that voltage you will maintain that maximum power point. So that you will, so through that voltage control, you try to control the DC-DC boost converter. So it will make sure that output of the DC-DC converter, you maintain the maximum power, and you can utilize whatever you want to utilize. Okay. So and also it improves efficiency and operational flexibility. Okay. Now another way of coupled system, as I am telling, AC coupled system. So AC coupled comes when you want some kind of grid integration, or maybe what we discussed in the previous lecture, wind energy system fed electrolyzer, because wind energy generate AC. Okay. Definitely if you want to, even if you generate hydrogen locally also, you need to convert to DC. But even at grid scale, where you have batteries or solar, wind, and suddenly you want to have the electrolyzer in between, so you will take the common bus. You will connect a electrolyzer at a common AC bus, which you can say maybe the point of common coupling, where all other sources will be connected. So that point of common coupling power becomes AC, because it is connected to the grid. So that AC you bring, and to the downscale you make it to AC to DC, and then after AC to DC also, if the voltage level is not okay, you might end up with using another DC-DC buck converter for the electrolyzer use. So it enables energy storage, continuous operation, and better control. Okay. So because as I told, this AC coupled system makes more sense when you build the system at a higher scale, let's say community microgrid, or particularly when I say grid connected systems. So there we call hydrogen at scale. So there will be not single electrolyzer, there will be multiple electrolyzers that combinedly generating the amount of power at the grid level. Okay. So that is about the three, basically the three topologies available in the literature, and yeah. So this is one of those pictures only, like you can, if this is a directly coupling, you can, it's of course very high level schematic, but there are technology involved how to maintain this. So the paper I provided, you can go through that and to know more how the operation happens. Okay. This is a directly coupled. If you have a DC bus system, then you will have a DC-DC converter. Sometimes the storage system is optional. If you can have a storage, it's okay. Storage means battery, kind of battery energy storage. And if you have that, you can, because what happens, hydrogen production, if you directly taking from solar, solar power is not available at night. So hydrogen production will be stopped. So that time battery can be a backup. But having said that, if you can imagine how much cost is also involved here. Battery is not a small cost, right? So hydrogen even cost not small cost. So depending upon whether you require hydrogen production at the night, you have an objective there, then it makes sense you make a storage system available that can capture the solar power in the daytime in the form of charging, and the night time in form of discharging. It can supply power. So that part you can disconnect. Solar power is not available, power will flow from storage to electrolyzer, and that you can utilize for hydrogen production through discharging of the battery. But that is if conditional, if it is required. Okay. So that is again DC coupling. Now for AC coupling, as I told, you see that power system. That power system basically the grid connected system. There will be several other sources, loads will be connected, and there will be a bus, AC bus, from where you all the resources, if you have a wind, solar, storage, electrolyzer, you take as your connection points, and depending upon what is your required supply, you either use directly those power or you convert to AC to DC. So that power system again will be not small. So then in that scale the electrolyzer capacity also will be very big. Solar PV will be not like a rooftop solar, it will be a big solar power for solar plant. Storage also will be adequate depending upon the demand requirement. Okay. So in that case also you can also expect some kind of ancillary services, which we will discuss tomorrow. I will so tell you from the electrolyzer itself. So here I want to give an example before I start. So as I told, if you want to give some grid services, let us say frequency ancillary services, okay, and in mostly frequency in transmission line is related to active power, right? All of you know, right? And voltage is controlled by reactive power. Transmission level I am saying, and most of our Indian grid is transmission level I am talking about. So if a solar individually has to give some frequency ancillary services and suddenly under frequency happens, solar is already at MPPT. So frequency active power is related through some droop characteristics. Droop means they are not directly related. So if you are, it is like a droop, you can say inversely related type. Okay. So if under frequency happens, so grid expect the solar power, it will give some active power, because frequency drops, you give some more active power. But if you already maintain your MPPT, you don't have any capacity to give that active power, right? So that's why what nowadays utility operator is asking, you come off the solar PV inverter design so that you always have a capacity of 15%, 20% extra to your rating, okay, and you make sure you also have the capability to run at a minimum power to your MPPT. So MPPT point, as I told in the top point, right? Suddenly if my MPPT point drops, but my capacity is MPPT, but I run at lower power, so I will have some power reserve capacity, right? So at that power reserve capacity also you should be able to operate. So that frequency drops, that power you can give to the grid. And of course, as professor was telling, this all are tariff based. So utility operator will give you some kind of benefit, some kind of benefits for providing these services. But the interesting why I am telling, that is one thing you can get, but another disadvantage, the moment you drop from the MPPT, your expected power you cannot generate. So your solar investment what you did for 100% to run at 100% power rating always, but once you are dropping, you are not generating the expected power every day, right? So to mitigate that, this hydrogen can help the solar power. So what will happen, solar power will make it MPPT, hydrogen will do that job of controlling its active power based on the frequency. That's why we call it as a flexible load, not a simple passive load, R load or inductive load. So it will help to maintain the solar at MPPT, but when frequency event happens, it will give the active power, because this electrolyzer will not be required to operate always at 100% capacity. It can operate between 30, 50%, 60%, depending upon how much hydrogen. You will definitely not require hydrogen production 24/7, right? So you can, if your hydrogen production or hydrogen demand is less, you definitely drop down your power consumption capacity, and when it is required, you can again increase. So that kind of demand flexibility this hydrogen brings into the grid. That is the whole objective of this workshop or the 5-day program. At grid scale, this hydrogen electrolyzer can be a good, I can say in layman's language, good friend for renewables. Being a load, it can support the grid, because renewables are basically generating sources, right? Being a load, being a flexible load, and when I say flexible, basically demand flexibility. Like grid demand more power, it can give. Grid demand less power, it can reduce the power. So it will not hamper the power generation from the renewables. Okay. So that is the another importance. So basically, what are those services? I will tell in my lecture next, when I will talk about some kind of grid code standards for this IBS. Okay. So you can see, I mean, I have taken something from the literature, so it is generic. So as I told, PV power generation is not smooth like synchronous power, right? PV is highly dependent on weather. So temperature changes, power will change. And temperature, if you see, your morning to evening temperature profile highly fluctuate, right? Even Dharwad is, you can see every 15 minutes you don't see, you cannot predict whether it will be raining or it will be sunny. So in that perspective, once this profile of temperature irradiance change, then our power output will definitely change. And that power and output changes, that will impact, because you are feeding that power to the electrolyzer. So electrolyzer input power will highly fluctuate. So due to that fluctuation, electrolyzer membranes, that may undergo some kind of degradation, or some kind of any kind of abnormality can happen, because the power keeps on fluctuates if directly fed from solar. But what is the solution? If you are kind of a DC-DC power converter, you try to maintain that through MPPT. Through voltage control, whatever power fluctuate, voltage fluctuate, you bring into MPPT, so that hydrogen don't see that much power fluctuation once you have this MPPT controller. Then also it improves system performance during fluctuation. Partial shedding is one kind, right? Partial shedding, all of you know, right? So the PV panel, some PV panels are sometimes, if you have seen somewhere, it is inclined, right? So when the sun goes from east to west, and all sometimes you have cloudy environment, or some kind of, I mean, your total panel is not getting the proper intensity. Some part is getting full intensity, some part will get uneven intensity distribution over the panel. That you can say some kind of partial shedding impact. That will also affect the output power. Okay. But in that case, if you have this MPPT control, and you can ensure that the maximum power point you can maintain through some kind of control philosophy, then it makes sense, and your hydrogen production will not be impacted that much. So MPPT control method, there are so many, starting from the traditional to the upcoming technology. Even this machine learning algorithms also people are using. There are some example I have put. The traditional is perturb and observe algorithm, P&O. INC stands for, so the previous paper I showed you, that you can open and see each of the techniques. So basically they are using different kind of genetic algorithm or machine learning techniques to maintain that MPPT point. Okay. So different intelligence techniques have their own objective, based on, basically they are like their own mathematics. So who are from machine learning background, these are same philosophy, but its application is how to maintain the MPPT here. So particle swarm optimization, different optimization based techniques are also available, genetic algorithm. Then intelligent means fuzzy logic, artificial neural network, and hybrid. Sometimes you traditional matter you put in close with the intelligent techniques. So you don't want to the classically doing the control, MPPT control, you attach the machine learning technique, so it will make it automatic and more intelligent controller. Okay. So these are some of the classification. This is already I told, no need to discuss what are the types of DC-DC you can use, isolated, non-isolated. And this is also the requirement for power electronic inverters, power electronic converters. This is also we discussed when we were discussing DC-DC and AC-DC. So one of the, with the, as we have less time, I'll say you only one case study. It is in Australia. So they have a 2 megawatt solar PV power plant, okay, and to that a 1.044 megawatt PEM electrolyzer, polyelectrolyte membrane electrolyzer is connected. Along with that, there is a 200 ampere battery energy storage also system is connected. And this electrolyzer of 1.044 is not a single electrolyzer. There are 6 PEM electrolyzer connected in parallel, generating total power of 1.044 megawatt. So what is the power of each electrolyzer? 6 are generating 1.044. So what is the power of each? By 6, right? The parallel combination I am telling. Now the question is, this case study states how to coordinately operate between these 5 electrolyzers. Let's say one power demand comes, not to overload any of the electrolyzer beyond their capacity. So coordinately operating these 5 parallel connected electrolyzers. So this is about that case study. So the structure looks like this. So you can see the right side electrolyzer 1, unit 1 to 6, all are identical, and power rating also, the power electronics point of view also they are equal. And in the left side you have a battery storage and you have a solar PV inverter systems. Okay, this is their total system architecture, you can say. Okay. So they call it industrial green hydrogen production hub. Okay. So details you will find in this paper also. So what is their problem statement? Because renewable energy, as I told, they feel that it is intermittent and highly power fluctuates. So that fluctuating power, if you don't coordinate this electrolyzer properly, they might directly impact the hydrogen production or sometimes damage the hydrogen electrolyzer. Because they have to do, parallel electrolyzer you have to coordinately operate means each electrolyzer with some kind of protection strategy, right? Because power electronics are involved. If you see in the model, power electronics are involved, like buck converter, single stage buck. So once this power, because let's say one electrolyzer have a maximum limit or lower limit. So the protection scheme works like if you hit the limit, you switch off, right? That means if the power fluctuates too much, then it will directly hit the limit of each electrolyzer capacity, upper or lower. Sometimes it's higher or sometimes lower due to low power requirement. So this electrolyzer, or including the power electronic, has to be switch on and switch off frequently. And that frequent switching on and off will directly affect the membrane or the electrolyzer electrodes and all. What they observed. That's why in this there is a standard on and off technique which they call choppy control. So that face this kind of issue because they only set the upper and lower limit for each of the electrolyzer, and once they, due to high solar PV fluctuation, these limits, upper and lower limits of the electrolyzer frequently hit, and the electrolyzer keeps on switching on and off every time. It's a load, right? It's like R load, you switch on, switch off, RL load, you switch, like electrolyzer itself a load. There is a breaker, if you see in the model, there are breakers are there, right? Switch 1 to switch 6. So those switches are keep on and off. That means that's the input of buck converter, right? So due to that, the hydrogen production becomes impacted. So they told that they will come up with a robust power coordination technology. Okay, and how they did this? So this is, I was telling about the MPPT curve. Whoever don't know, so the curve says the x-axis is the voltage and the y-axis is the power. So that peak point of that valley you basically call the maximum power point tracking. And if you can see, this kilowatt per meter square is what I told, irradiance, right? So that irradiance itself directly affect how much maximum power you can generate. Also it varies on the temperature, but not shown here. So PV characteristics, this is their what they studied. So this is their electrolyzer model. Already we discussed, I think, right? Remember or forget? Tomorrow is the exam, right? Okay. So please go through. This is the dynamic electrical equivalent model, right? Then what is their methodology? So first they model the PV, then electrolyzer, then some storage, and this is like different design thing they did step by step. Then what they did, sorry. So if you see the first graph is basically there is a slow variation and high variation. Okay, so due to that, how much the solar power is keeps on changing, depending on that the electrolyzer power input also keeps on changing. Okay, so that change, this they put two variation, one is very fast variation, one is very slow variation. And what they did, as I was telling, the classical existing what is choppy control, they call start stop, like initial, frequent start and stop. But what they told, that instead of giving a single lower limit, higher limit, make it different zones. Okay, so you switch between different zones between lower and higher, so that you need not to be every time switch on and off. So what I mean, so let's say my electrolyzer is 100 megawatt, so I keep my lower limit as 10 megawatt and 90 megawatt. That is the startup control. If the power fluctuation above 90 megawatt, I will tell switch off, or power below 10 megawatt, I will tell switch off. Instead of doing that, I will put 3 layers in between, 10 to 30, 30 to 50, 50 to 90. And I will operate, let's say, at when there is a no requirement, operate in the low zone. And once the solar goes up, power will come up, power consumption requirement is up, then you slowly, very smoothly change between different zones, so that you need not to directly wait for high power then switch off. Okay, so that is the thing they brought here. So they divided into low, high and overload. So this is that conventional choppy. So depending upon you can follow that paper reference 4, of course. So depending on one electrolyzer, you see their power rating, the expected power and their rating, you match. If they below minimum and above maximum, you trip them. But instead of this, the segmented choppy is like, as I told, there are different segments. So it's basically a logic, if else logic, nothing else. So this logic they implemented in terms of different segments, high, low and the overload conditions, and they run that. And if you see, this is the result of a choppy control. If you see, the red and green are overlapped. Okay, so the red is the reference power signal for a electrolyzer, and the dotted green are the power consumption. So this is, as it is like a there is very classical choppy control. If you see, the solar power is changing, the red color signal also changing, because the more power you generate, more you have to consume, right? And due to the power controller, this red color is also following that, and you can see there are very big steps the electrolyzer is facing in terms of power, and that due to that it is also going through that switch on and off condition. And in comparison to, if I see the segmented one, so if you see, the one operating zone to other operating zone is not a step, it is a smooth one, because it has passed through different layers within the low and high. Okay, So that's why they achieved this. They told that with this segmented power coordination control, they achieve a better smooth power coordination among the hydrogen electrolyzer, and that they enhances the reliability of their hydrogen production. There are other results are there, but I will skip that. We are already time. Yeah, so I want to say that this segmented control there improve the system reliability and hydrogen yield, hydrogen production, and of course this is one of the case study I showed, but at least you understand what are the system architecture, what are the things required, and what could be it. Your study can be at the device level, your study can be at the system integration level. So depending upon that, your objectives, you can work on various aspects. Okay, thank you.
Thank you, sir. Any questions from the audience?
If no questions, we can move for lunch. Okay, please.
Sir, there were two topologies, DC coupled system and AC coupled system. Out of that, in AC coupled system, it allows the integration with the grid, and for DC, it is for the efficiency and enables MPPT. So which one should we choose if we want to integrate, means DC, what is the advantage if we want to use it in the grid part?
No, definitely DC has more advantage because we are going towards DC. But currently still our some of the generation are AC and our loads are AC. We are still for grid integration, our grid itself AC. So as I told, different architecture, those are highly subjected to your objective. Let's say you are just for hydrogen production for some end uses, you want to generate locally in the form of, let's say, kilowatt or maybe less than kilowatt. So that time you can go with a DC because at the end of the day electrolysis happens with a DC power supply. So but if you are aiming for a big investment at the grid scale and you want to integrate to the AC grid, definitely you go for AC coupled because you cannot pass the DC or consume DC power directly from the AC grid. So you have to have some kind of conversion in between. Yes. Microphone.
Two questions, one clarification. You mentioned about hydrogen storage electrolyzer being a flexible load. So does it mean that it starts feeding power back to the grid, or it reduces the output? What did you mean there?
Okay, so in this case, when I say flexible load, is basically I consider it as a load. So load means it is only sink of active power. So but that sink is not fixed. So that sink you can, because you have power electronics and control involved, that sink you can make it a relation to the frequency services. Let's say I am giving I have a AC/DC rectifier, active front end rectifier. I want to control it as a grid following or firming. So from there I can control my active power consumption based on the grid frequency. But of course, its counterpart is called a fuel cell. So that hydrogen what you produce, you can back it, make it inject to the grid through a fuel cell, where you give hydrogen as an input. Then it's like exactly opposite operation of hydrogen. And there are certain technology are available which we call the reversible electrolyzer, where you can do both electrolysis and fuel cell operation in a single cell. So but here of course grid ancillary service I told in meaning to the flexible load, meaning to the sink of active power. That's how you can give some service to the grid.
Okay. And second is this control and operation. How if we have a solar, just a battery for storage, or other way is to have hydrogen electrolyzer. In the end, both of them have DC port as the interface to the outside world. How does the control and this operation changes when we bring a hydrogen electrolyzer into the picture compared to if you simply treat it as a battery?
Yeah, so the main two aspects different between hydrogen electrolyzer and the battery. One, I will again repeat that PQ curve. So if I draw my P active power and reactive power axis, so as I told, electrolyzer can operate being a sink of active power, but it can source both reactive and source and sink both the reactive power. But for a battery, as we know, it is a bidirectional device. It can operate in all 4 quadrants. That is one of the system characteristics. Another important characteristic is hydrogen electrolyzer is a low voltage, high current device. But I think battery you can still operate with a normal DC voltage. So even if they share the same DC bus, which is compatible with battery, you might require another stage of DC-DC step down to feed the electrolyzer. Yeah. Thank you. Any question?
Any
Lunch?
questions?
Okay.
Thank you, sir.
Lunch break. Thank you, everyone. We will meet 2:30 for the hands-on session. Okay. Thank you.